Hello and welcome to Decision Support Systems for Managers. We are into Module 2, Lecture 3, and this module deals with models and decision support systems, and today we will deal with solution techniques, linear programming for optimization. These are the concepts covered in this module as we have mentioned earlier. What is a structured problem, what is a semi-structured problem, what is a model, classification, purposes of modeling. All these we have covered, and we have said structured problem is very routine. We can put the problem into some predefined structure and get a mathematical model out of it. Semi-structured, we can do it partially, balance is left to the ingenuity, and newer models can come in place. Okay. And what is a model? Model is a mathematical expression of real life situations, and we can replicate them in the real life. And classification of the models, we have done it some choice model, sorting model, ranking model, etc. Purposes of modeling basically to enable us to take timely decisions. Now, what are the solution techniques possible? Optimization, heuristics and simulation. Okay. Today we will deal with this one we have covered. Today we will deal with solution techniques, optimization, heuristics and simulation, of which today we will deal with only the first part, that is solution techniques, optimization. Okay. Now, optimization, normally we will take care of three: linear, integer and non-linear optimization. Okay. Today we will deal with linear optimization or linear programming, which is commonly called linear programming optimization of problem. Now, linear programming, if you see, it is, I would say, 95% structured. Some people will say no, it is 100% structured. It is a very time tested model. I agree 100%, fully agree. It is a fully structured, time tested model, linear programming. Why I am saying semi structured? In the sense that partial, little bit, 5% is sensitivity analysis, that within a range this is the output possible. You can say that that is also a part of fully structured models. I agree with it, the way you want to look at it, it is up to you. Okay. So, linear programming, normally we will call it as a fully structured model. Okay. So, let us see what do you mean by that. A company manufactures two bags that goes through the following processes. Company manufactures two types of bags that go through the following processes: cutting and dyeing the material, sieving, finishing, okay, inserting the umbrella holder, the club separators, inspection and packaging. So, cutting, sieving, finishing and packaging. These are the four things that go in: cutting, sieving, finishing and inspection, right. Now, this is the time taken by each of these types of bags. What it is saying is that two types of bags are getting manufactured, one is standard bag and one is deluxe bag. Now, there are four departments, cutting, four processes: cutting, sieving, finishing and inspection, cutting, sieving, finishing and inspection. Now, a standard bag takes 7/10 of an hour. A standard, if you see, I am moving the cursor, and if you see here, a standard bag takes 7/10 of an standard bag takes 7/10 of an hour to manufacture in the cutting and dyeing process. Deluxe bag takes 1 hour. Sieving takes half an hour for standard bag and 5/6 of an hour in the deluxe bag. Finishing takes 1 hour for the standard bag, and deluxe bag it takes 2/3 of an hour. Okay, and inspection takes 1/10 of an hour in the standard bag and 1/4 of an hour in the deluxe bag. Okay. Now, the profit is ₹9 and ₹10. Question is, how many pieces of these two types of bags should the company manufacture? Now, if there was unlimited everything, let the company manufacture as many as they want, but that is not the case. There is a constraint, or there are constraints. What are the constraints? Let us take this example. A company manufactures two bags that goes through the following processes: cutting and dyeing the material, sieving, finishing and inspection and packaging. Okay. Now, if you see cutting and dyeing takes about 7/10 of an hour. Two types of bags are manufactured, standard bag and deluxe bag. Cutting and dyeing takes 7/10 of an hour, deluxe bag takes 1 hour. Sieving takes half an hour, deluxe bag takes 5/6 hour. Finishing takes 1 hour, 2/3 hour, 1/10 hour, this thing. So, if you see that normally we are saying the deluxe bag takes a bit more time, right? Deluxe bag takes a bit more time. Now, okay. So, the profit for every bag is ₹9 and deluxe bag is ₹10, right. How many pieces of these two types of bags should the company manufacture? The question is that this cutting process has a 630, 600, 708, 135, 708 and 135. Okay. Now, this cutting and dyeing, this is the time taken for one bag, but this cutting and dyeing process total hours available is 630. Total hours available is 630. Total hours available for sieving is 600, finishing is 708, inspection and packaging is 135, right. Okay. So, what should be the So, what should be the model? Okay. So, this is the first one that we are dealing with. Okay. Optimization techniques, linear. What did we say? We said the company manufactures two types of bags. Each bag goes through these 4 processes. These are the 4 processes. This is the time taken. Profit is this, this and this. Okay. Now, so let us go by it. So, profit is 9 and 10. So, what is my objective? My objective is to maximize this profit, right. How many standard bags should we manufacture? We do not know. So, let us keep it S. How many deluxe bags should we manufacture? We do not know. So, let us keep it at D. What is the profit? Total profit then 9 per bag into S bags manufactured, that is 9x1 or 9S, and 10 per bag into D number of bags manufactured. So, 10D or 9x1 plus 10x2. Okay. What are the constraints? Constraints is cutting takes 7/10 hours. So, 7/10 of S plus 1 of D lesser than equal to how many hours were available? 630, right. Okay. 630 cutting hours was available, right. Next one was, if I am correct, 600. For sieving 600 hours are available, half of S plus 5/6 of D, 1 of S plus 2/3 of D. I think this is 708 if I remember correctly, yeah, and 135. This is 135. Okay. So, is this clear? My model is maximize 9S plus 10D, maximize 9S plus 7D, subject to 7/10 hour into S bag, 7/10 hour per bag into S number of bags manufactured, 7/10 hour per bag into S number of bags manufactured plus 1 hour per bag into D number of bags manufactured, and so the total hours available is 630. Total hours available is 630. So, this is my linear programming model. Okay. Let us go. So, you see this is the model in the proper form, max 10S plus 9D subject to 7/10 of S plus 1/10 of D, half of S plus 5/6 of D, 1 of S plus 2/3 of D, and 1/10 of S plus 1/4 of D less than equal to 135. Okay. So, this is the model. Now, the question is how to solve this. How do we get the quantity of S and the quantity of D? How to solve this? Okay. So, let us now go through that. Okay. Yeah, the graph. Now, what was my equation? Let us take one 7/10 of S plus 1 D is less than equal to 630. 7/10 S plus 1 D is less than equal to 630, right? When S is equal to 0, D should be equal to 630, right. For simplicity purpose, we will make this as equal, right. When D is equal to 0, x is equal to what? 6300 by 7, that is equal to 900, 7 9s is 63. So, for first constraint, constraint number 1, what did we get? S and D points, S is 0, D is 630, D is 0, S is 900, right. These are the 2 points that we get. Understood? First equation was this 7/10 S plus 1 D is equal to 630. When S is equal to 0, D is equal to 630. When D is 0, S is equal to 6300 divided by 7, that is 900. So, what are the 2 points? S 0, D 630, D 0, S 900. This is the first equation point. Sorry, let us go to the second point. Let us go to the second point. What was the previous equation? Half S plus 56 D less than equal to 600. Half S plus 56 D less than equal to 600. Okay, let us go. Sorry, half S plus 56 D less than equal to 600, right. Okay. So, when S is equal to 0, D is equal to what? Three six zero zero by 7. Yeah, sorry, 3600. I am so sorry. I am so sorry. This 3600 by 5, right? Okay. 36. Oh, sorry. Anyway, 3600 by 5, that is equal to 3600 by 5 is equal to 720. When D is equal to 0, S is equal to 1200. Okay. So, my next equation becomes S and D right. Okay. Right, half S plus 56 D is less than equal to 600, S 0. So, D becomes 3600 by 5 720 and D is this. Okay. So, in this way we can get the list of all equations. Okay. Clear? So, for equation 3 I will just for equation 3 we will get 0 1052 and sorry 1062 1062 and 7080, and for equation number 4 we will get 0 540 1350 and 0. Okay. Clear? So, this is the okay. Okay. So, what I will do is I will erase this, and is it clear? First, if you solve these 4 constraint equations, we get these values, okay, right. So, now we will do a graph of these, we will do a graph of this. Let us see. Yeah, thank you. Yeah, let us see. So, we first equation we got S 0 D 630 D 0 S is equal to 900, right. Second equation we got S is equal to 0, D is equal to 1 0, sorry, D is equal to S is equal to 0, D is equal to 720, D is equal to 0, S is equal to 1200. These two we solved. Okay. Now, for the third constraint we get S is equal to 0, D is equal to 1062, D is equal to 0, S is equal to 708. For 4 we get S is equal to 0, D is equal to 540, D is equal to 0, S is equal to 1350, right. Now, let us draw a graph. Okay. Let this be S and let this be D. Now, what is the maximum value of S is 1350. So, let us go at 0, 500, 1000, 1500. What is the maximum value of D? D gets me at 1062. So, let us go for 500, 1000. Let us take the first equation S 0 D 630. I will use different color. S 0 D 630. S is 0, D is 630. Okay. D 0 S 900. D 0 S 900. This is my equation 1. Okay. Then S 0, let us use another color then. Let us use a green. S 0 D 720. Okay. D 0 S 200. D 0 S 1200. Let us try the third one, S 0 D 1062, somewhere here, D 0 S 708. This is equation 3. Then S 0 equation 4, let us use a fourth color. Let us use this. S 0 D 540 and D 0 S 1350. Okay. So, this one is my equation 4. Okay. Right. So, if you see, what was my objective? Sorry, what was my objective? My objective was maximization, right. So, my common space, so let us go back again, if I can, I do not know whether this color will work. My sorry, my common space is this one, right? So, I have 2 points. Okay. So, I have these two feasible points, right, of whichever is maximum I will get it. Now, what are these two are the intersection point of these two lines, line 4, line 1 and line 3 and line 1. Okay. So, if you can solve these two simultaneous equations, you will get a value for this, for both these, and the value for S and D, whichever one gives me the maximum number, that is the maximum profit. Okay. So, if you solve this, you will get S as 540 and D as 252. Okay. So, this is the way by which you solve a graphical solution. Okay. Now, I have a question. If you solve this you will get. Okay. You will get 540 S we have manufactured and 540 S we have manufactured and 252 D we have manufactured, right. So, 7/10 of hour per bag into 540 bags, 1 hour per bag into 252, that is equal to 630 hours, right. Similarly, half hour per bag into 540 bags plus 5/6 of per hour into 252. So, this is basically the number of hours required. What was the hours available? 630, 600, 78, 135. So, here hour required 630, we had 630, so unused is 0. 480 hours were used, we had 600 hours. So, 120 is unused. 708, 708, 0. 117 hours were used, we had 135 hours. So, 18 hours were unused. These unused hours, these unused hours is called as slack variable. These unused hours is called slack variable. Okay. Just this, nothing else. Unused constraint, unused quantity in a constraint is slack. Okay. Just remember this thing, unused is slack. Okay. That means we do not need this. This is one managerial decision. You can find out wastage, you can find out where to reduce cost, you can find out where to reduce cost because this is unused. You can negotiate with the suppliers, give me less, negotiate with the finance department. All along we have been purchasing more, a new machine has come, this is not required, reduce the number of maybe working hours. Okay. So, this is the use of slack variable. Okay. We will take on with another example in the next class. Okay. These are the references. Thank you.